Thanks. Thanks a lot for this introduction. Good afternoon, everyone. And thanks for inviting me to give this seminar. Very happy to have the chance to present indeed what I've been working on since many years now. So let me start the sharing of my presentation. You should be seeing the slides, correct? Let me adjust all the various pop-ups on the screen. All right. Good. So indeed, what I'm going to present is an overview, essentially, the status and the prospect for Higgs boson pre-production, focusing, essentially, I would like to show you, first of all, what it is, what is the role of the self-coupling that we'll discuss a lot during the next 40, 50 minutes, and the Higgs in the standard model, how we search for the Higgs, the LHC, how we use the Higgs as a probe for new physics, and then what are the prospects essentially for the short, medium, and long term to measure this process. So just to get started and get an idea of the role of the broad-angular Higgs mechanism, the scalar potential in general, why this is important in the standard model, how about the self-coupling and its relevance, and finally, the Higgs production at the LHC. All right, so you've probably seen this picture many times, so this scheme, but I wanted to recall that why the scalar sector is important, why is it the center somehow of the standard model. In the standard model, we can identify essentially a structure with a gauge sector, where electroweak strong interaction are explained by imposing a local gauge symmetry, so essentially a very simple and beautiful symmetry to the fundamental Lagrangian of the standard model. And to complete this, so to actually describe what we observe in nature, so the mass of the weak bosons and the mass of particles in general, we need to complete the standard model with a scalar sector to preserve this gauge invariance, but give mass to the particles. And this is done in the standard model, so in the broad angular Higgs mechanism, by essentially introducing a complex scalar doublet of fields, phi, which would be here, which is subject to a potential with a vacuum expectation value that is non-zero. So the potential has this shape that is written here, so it's just represented by this sketch. And you see that upon there's a minimum of this potential where the vacuum expectation is not zero. So this implies that the electroweak symmetry is spontaneously broken. So this is the broad angular Higgs mechanism. And then once you get to a ground state, you get additional degrees of freedoms, which become the W and the Z boson polarizations. So the extra degrees of freedom hidden essentially in this symmetry. And then you get excitation of the residual degree of freedom, so the quantum of the field, which is the Higgs boson. And this is the broad angular Higgs mechanism. It gives the mass to the W and the Z bosons. It gives masses to the fermions via Yukawa interactions. And essentially, it's a necessary ingredient because it regularizes the theory at the electron volt scale. And as you can see, all the properties of the standard model, of the scalar sector, are determined by the shape of this potential, shape which is encoded in this parameter lambda, which is here, lambda, and then it's connected to the Higgs boson mass through essentially 2 lambda v squared. All right, so upon electroweak symmetry breaking, the potential can be rewritten at the minimum of the potential. So after we go to the ground state, and then we get a term which is the Higgs boson mass. It's here. A cubic and a quartic interaction, so H cube and H fourth, that essentially transform into represent a trilinear and a quadrilinear Higgs boson interaction, and then a constant which contributes to the vacuum energy density. We won't cover it so much because it doesn't matter has no implication for particle physics, but has strong implication, for example, on cosmology, because it contributes to the vacuum energy density, and it's much larger than the observed density, which corresponds, for example, to the expansion of the universe. So we'll mostly focus on the linear coupling, is our main character for this seminar. And the strength of the linear coupling and quadrilinear coupling, so lambda triple H, lambda quartic H, is exactly lambda in the standard model, and can be computed because it depends just on the Higgs boson mass, on the vacuum expectation value, and it's about 0.13. So the self-coupling is directly connected to the shape of the scalar potential, and this is what we want to measure. Now, we know we start to know the Higgs boson quite well at the LHC because we have discovered it in 2012. We've measured its mass, and essentially at the per mil precision level, you see here two recent measurements by Atlas and CMS, and essentially we know the Higgs boson mass indeed at the per mil level. So we have a very good prediction on the value of lambda. We know very well most Higgs boson couplings because as you see here, for example, in this plot from Atlas, we see that the Higgs boson does couple proportionally to the mass of the particle it couples with. It's unique property. It's really Higgs boson in action here. What we do know is the self-coupling, which could very well fit in the same picture because it's also proportional to the mass of the Higgs boson. So this is to say that there's a very major experimental effort ongoing to characterize the Higgs boson, and the goal is to measure lambda. It's one of the next key goals that the scientific community in particle physics has for the exploration of LHC data. All right, so then you may wonder why it's important. We know so many couplings. This is already predicted, so it's just another coupling to measure. And the point I wanted to make is that actually the shape of the scalar potential, so the value of lambda, is connected to many open questions of both particle physics and cosmology, essentially because it relates to a very fundamental and basic structure of the standard model, which is the scalar potential. So this sketch here represents essentially the value of the potential once we describe it at the ground state, so at our around where the Higgs field is at the ground state. And what you can see is that the value of lambda, of course, is sensitive to higher order correction, so to running, and depends on contribution from other particles. Now, depending on the actual value of these contributions, we could be in a situation where our vacuum is stable, so the minimum that we have is the true minimum, but could also be a situation where it's unstable or metastable, depending whether another minimum exists, for example, in the metastability case, which is favored. And now the fact whether we are in a situation that is stable or metastable essentially depends on the contribution from, for example, top quark mass, top quark corrections. And you can see here how the running of lambda is computed depending on the value of the top mass and of alpha. Now, once lambda crosses the value of 0, so becomes negative, we enter in a metastability situation. And it seems like from most recent determination as summarized here, that we live just at the edge of metastability. So the best fit, given the value of the Higgs boson mass that we measure and the value of the top quark mass, is right within a couple of sigma at the edge of stability, but lies in the metastability region, which means that our universe is not stable according to these measurements, which means that it could transform into into a different vacuum, and clearly calls for some mechanism that could stabilize this vacuum and make the universe stable in the state that we observe now. For the same reason, the scalar potential is linked to the electroweak symmetry breaking phase transition, and the value of lambda determines whether it's a first or second order transition, and whether baryogenesis could or not happen through the phase transition electroweak symmetry breaking. And as we said, it also relates to the cosmological constant. So somehow this self-coupling, so the value of the shape of the scalar potential, is very much at the center of many open questions in our field, and that's why we want to study it with the best precision. So we come to the point of how we can measure this value. And there are essentially two complementary strategies that we can adopt in the LHC. One is to measure it directly. So we always want to search for a vertex which connects three Higgs lines. We can do a direct measurement in HH. So essentially we produce pairs of Higgs bosons. It's direct, so theoretically it's very clean. The process is very rare, as we will see. So experimentally it's rather challenging. On the other side, we can use indirect measurement of single Higgs. So we produce single Higgs bosons, but we exploit the fact that higher order correction can involve linear coupling. And this, of course, implies stronger theory assumption because you need to disentangle next reading order lambda effects from other couplings, from new physics, from whatever could modify these loops. But it benefits from the larger single Higgs cross-section. We see it's bigger than the Higgs cross-section. So we have pros and cons on the two sides. And essentially, as you see, we are trying to combine both strategies, so we maximize our sensitivity to the self-coupling. And so coming to the Higgs production at the LHC, our direct way to measure the self-coupling, essentially, you see summarized in this figure the various production modes as computed at NLO. The black bar is gluon fusion. So gluon fusion is the leading production mechanism in the LHC, and it proceeds at leading order through these two diagrams. One is called a triangle, and it involves directly the self-coupling here. And one is typically called the box diagram, doesn't involve the self-coupling, and these two have a very strong destructive interference, which in turn implies that the production cross-section for Higgs boson pairs at the LHC is very small. So it's about 30.7 or 24.1 femtobarn at 13 and 13.6 TeV, which are the two energies that now we are exploring at the LHC. So it's a dominant production mode, but it's very rare. In the full Run 2 dataset, we have about 4,300 Higgs events. And this cross-section makes it experimentally very challenging. We see searching for such a rare process is not easy, essentially experimentally. All right. So how do you use it to extract the self-coupling once we can measure the Higgs production? The first thing is, of course, the total cross-section. And you can see the variation of the total cross-section here as function of kappa lambda. We typically use kappa as a sort of convention to define essentially a modified value of this coupling lambda normalized to the standard model prediction. So the standard model corresponds to kappa lambda equal to 1. And the gray curve is the gluon fusion prediction as function of kappa lambda. And you see that, of course, it's a quadratic function, which has a minimum around 2.5. The standard model has the cross-section we just seen. And essentially, we have an ambiguity in the total cross-section. There's always a symmetric point in kappa lambda, which gives you the same total cross-section. But then you can also use differential information. So essentially, how this cross-section is distributed as function of the invariant mass of the Higgs pair, because this is going to be dependent on the squared box diagram, or let's say diagrams which don't depend on kappa lambda, which is the contribution in red, on the triangle square, which is the contribution in blue here, and on the interference. And here you see why essentially the Higgs is so rare. It's because the interference is very strong and negative. So it cancels the largest part of the rest of the contribution in this amplitude. So by using differential information, so by trying to measure the Higgs at low invariant mass and high invariant mass, you can resolve this degeneracy essentially and be able to see the standard model or anomalous values of kappa lambda. All right. So in this sketch that we'll see in a moment, which is quite old, it's derived by leading goal. So it's just an illustration. But I wanted to show how important are interference effects, because these are going to essentially impact how analyses are designed and why we need to search for the Higgs using kinematic regimes which are both low in invariant mass and high in invariant mass. And what you see on the left is the distribution of the Higgs pair, so the distribution in arbitrary units. And on the right, you see the dependence of the total cross-section as function of kappa lambda, and the point is given by the circle. And as soon as you vary the coupling, you see you enter in the maximal interference region here, where there is a very big change in the shape of the Higgs system. Essentially, you move from a continuous shape to a two-peak distribution, and then asymptotically, when kappa lambda becomes very large, you move again to the same shape as for very negative value of kappa lambda. So essentially, experimentally, we need to be able to be sensitive to distribution of the Higgs system, which are very different, can vary a lot depending on our coupling, which is quite a challenge for the optimization of analysis, because you want to be optimal for the standard model, but also for scenarios where kappa lambda is different from 1. Okay, so now that we see why it's important to study the Higgs, I'll try to give an overview of how we search for it. Essentially, which are the decay channels we explore at the LHC. A quick look at the main experimental analysis, which would be 4B, BB tau tau, BB gamma gamma, and then the LHC Run 2 combined results. And then I think now we are lucky. We are really collecting all the results from the LHC Run 2. We are starting with the Run 3 analysis. We can look a bit back at the road that we have done, understand how we have improved, what can be done in the future, and then have a look at how these results are combined with single Higgs boson production. Okay, the machine, of course, that we use is the Large Hadron Colliders. Don't think it needs much introduction, but essentially is designed to deliver proto-proto collision at 14 TeV. So far, it has been operated at 13 in Event 2 and 13.6 TeV in Event 3. It's designed for luminosity, instant luminosity, which is 10 to the 34 centimeter minus 2, 7 to the minus 1, which has already been exceeded. So we are really going beyond the initial design of the machine. What I'm going to show here is essentially from the 2016 to 2018 LHC dataset, which corresponds to about 140 inch femtobarn. As you can see, just in these 3 years, there has been a very impressive program of research by Atlas and CMS on single Higgs and DAI, which is the topic of this seminar. Now, which decay channels? We are lucky; we have many decay channels we can explore to study the Higgs boson. So we have square of this number once we want to explore the Higgs. Now, this plot essentially summarizes the various decay channels of the Higgs system. And the check marks are the results which are currently public at the LHC Round 2. And you see we are covering essentially all the phase space. Now, most channels tend to focus on the decay of one Higgs boson to either a pair of B quarks or a pair of W bosons. This is because the process is reverse. So you want to keep the branching ratio high enough to make sure that you can see enough events. And the choice of the other decay, the decay of the other boson, is essentially a trade-off between the purity that you can get in the analysis and the number of events that you can detect, so the branching fraction. And we'll see these two things tend to compensate. So we have many channels which have comparable sensitivities. They're not really a golden channel, but there are many channels that we benefit from combining and to have a common exploration. And then we start to cover more and more area. For example, by combining all these channels with the W's, tau, and Z's, we can do multi-electron analysis and use them to expand even more the phase space that is studied at the LHC. As you can imagine, this brings, in some sense, channel-specific challenges. So, for example, analysis which involves photons or taus have specific challenges for these objects, and common techniques, for example, for the X2BB decay. So, in short, there's a very broad experimental program that is brought forward by Atlas and CMS, and I'll try to give an overview of this analysis. I won't cover all of them because it will need just another seminar for the analysis and very more, but I'll try to show a bit the key channels in this plane. So to get started, we can go from the channel that has a high branching fraction but a low signal to background ratio, which is the X to 4B. And the first distinction we have to make is the topology of the decay, because depending on the PT of the Higgs bosons, you can have at low PT, let's say below roughly 300 GeV, two B quarks that are well separated. So you really constructed to the Higgs boson pair as 4 separate jets. This is the largest fraction of signal because typically the PT is not very high in the Higgs production, especially in the standard model, but it has a large QCD background. So the challenge in the triggering and identification of these events. And on the other side of the spectrum, you can just focus on Higgs boson with very high PT. This, thanks to the Lorentz boost of the decay, the two decay products will be collimated and can be reconstructed as a single jet. Typically, the value used is 0.8 for CMS analysis and 1 for Atlas analysis. So you get 2 boosted jets. Essentially, you have an acceptance which is the order of a few percent to the standard model signal, but the backgrounds are suppressed. So these two things, again, tend to compensate. And if you search, for example, for a new particle going to the Higgs, this is the leading channel for, let's say, beyond the TeV invariant mass. So it's also the favored part of the spectrum for the Higgs invariant mass. Of course, there's a gray area or orange area in this plot, which is where the two things start to overlap. So there's overlap between the searches, can be optimized in the analysis. And by using this, you can essentially optimally explore the full phase space. So now if we start on the resolved analysis, the X to 4B, this is how the X to 4B events look like. You can clearly see the 4 jets, and you can see maybe a muon, which is producing a semi-electronic decay of the B, and the deposit in the calorimeter. This is an event which is selected by CMS with the 2016 dataset. It's the most abundant final state, and as we said, this decay channel contains about 1,400 events in the full Round 2 dataset. But you have a very large multi-jet background because it's very easy to produce multiple jets at the LHC. So here is how we try to select our events. First of all, in this case, we are under resolved channel, so we target a fully resolved topology for jets in the event. And we rely, starting from the online, so from the trigger, on BD jet triggers. So the high-level trigger will select events containing bjets to start to reduce the amount of QCD and try to keep the threshold sufficiently low. And then the key is to start to categorize the events. So events are categorized by production modes, are categorized by kinematics, again, by low and high invariant mass, by being standard model and BSM-like. This is done to make sure that the analysis is optimal to both standard model hypothesis and anomalous coupling, anomalous kappa lambda hypothesis. You have an ambiguity because you select 4 jets, so you need to find a way to pair them properly. And typically, this is done in a way that gives you the good reconstruction of the Higgs peak without bias in the background distribution. For example, in CMS, you select the pair which will give the minimal distance from this diagonal, so the difference in mass is minimal. So you are squeezing your events along this axis, as you see for QCD, but you don't bias your background to look like your signal by being under the signal region. In the Atlas analysis, you select jets by essentially taking the pair with the minima delta R. Essentially, you don't want to use the mass to reconstruct this information. And this gives clear definition of regions for the signal extraction. So you will look for a signal in this small circle here, and then regions for the estimation of the backgrounds around or for the validation of your background model shifted along this plane. So as we said, multi-jet is the real challenge for the X24B. There's an overwhelming multi-jet background, so we need very accurate data-driven estimates from the control regions. And this is done by taking data in regions with inverted number of bjets. It's 3 bjet for CMS because of the trigger, which requires 3 bjet. It's 2 bjet for Atlas because the trigger is looser in the number of bit tags. And then you use machine learning methods to learn how the 3B and data transform into 4B in this control region, and you apply this transformation to the actual signal region. So as you see, the improvement is dramatic. There is a very poor modeling if you just take the data from the sideband, but with this method, you can quite accurately describe your background. And then you separate the signal from the background either with, again, a BDT or a multivariate method to use the kinematic of the event, or in Atlas with a fit to the invariant mass of the X pair after categorizing events in various categories depending on the kinematics. And as a result, in this resolve analysis, the limit that is set is the sensitivity is about 8 times the standard model the X production cross section, with an observation of 5.3 for Atlas and 3.9 for CMS. If we move to the next channel, it's going to be beta tau. Beta tau is in a sweet spot because it has a good trade-off between the branch infraction and the signal to background ratio. And this is how a beta tau event would look like. First of all, tau is not a stable object, so we will decay in the detector, and we select 3 final states of the tau system, one with a muon and an hadronic tau, so tau H. Hadronic tau being a semi-leptonic decay where essentially the detector can just reconstruct the visible decay products. We call it tau H or tau had. And so you have a muon plus tau H, electron plus tau H, or fully hadronic final state. This is 88% of the decays, and it was seen to be the most sensitive set of final states. For the fully hadronic final state, of course, the challenge is triggering, a bit like in the case of 4B, because you always have jets in the final state. So an event looks like this. You have on one side 2B jets that recoil against the tau pair, so you will see 1 tau H, essentially calorimeter deposits plus tracks. You see the other object can be a muon, an electron, another tau H, and then you have a missing energy. So you have all the possible physics objects in a single analysis. You don't reconstruct fully the system because of neutrinos that escape the detection, but then there are likelihood methods to estimate the invariant mass of the tau pair, and essentially you can use them to suppress the backgrounds. But of course, there are backgrounds. These backgrounds are typically irreducible backgrounds, so backgrounds which end up in the same final state. TT bar, which decays to baby tau tau, or Z plus B jets with Z decaying to taus. And these are taken from simulation and correction in control region. And other backgrounds like bosons, ZH, Higgs plus B jets, which are smaller but still relevant, are taken from simulation. And then you have what are called instrumental background or reducible backgrounds, where other objects are misidentified as tau or as B. So again, can be TT bar, Z, multi-jet, which are taken from simulation and data-driven estimates. So again, we try to use, you see it's quite a constant to use the the property of the event to separate signal from the background. So here, the objects are first categorized, the events are categorized extensively by the tau decay mode we've seen, but also by production mode, by invariant mass, again, for optimal sensitivity to the self-coupling. And then you try to separate your background from your signal with multivariate methods. In Atlas, you see the output here of ability, which separates the signal from the background. In CMS with ADNN, as again, the idea is the same. You try to see your signal as an excess in the I bins of the discriminant, and essentially separate this from your background. The sensitivity is led by the full hadronic categories, even though the categories with the leptons do contribute significantly to the final number. And you see that, again, we are with a sensitivity which is about 3.3 times the standard model for Atlas and 5.2 times the standard model for CMS, with an observation of 5.9 for Atlas and 3.3 for CMS. So this number is still not so far from the 4B1. And we see many channels have similar sensitivities that will contribute in a combination. So now coming to the third main channel, so one which has a very low branching fraction but high signal to background ratio is the X2 BB gamma gamma. It's very clean, but it's very rare. So you need to maximize the acceptance and purity if you want to make a sensitive analysis. The backgrounds are essentially the diphoton continuum, diphoton plus jet continuum, and single Higgs. So the first thing is to use dedicated MVAs to suppress the background. As you can see in Atlas and CMS, you train this method to separate your background from one side to the signal on the other side. And then the events are categorized. So you take portion of this output to define high purity, medium purity, and low purity categories. And then these are further split again by low and high invariant mass, which gives optimal acceptance and maximal sensitivity to anomalous kappa lambda values, essentially. And to extract the signal, the most powerful signature here is the decay of X2 to photons, because the signal will be a very narrow peak in this distribution. So on the left, you see the combination of all events selected by CMS as a simultaneous fit between M gamma gamma and MBB, which is not shown here, but the sensitivity is driven by the M gamma gamma shape. On the right, the most sensitive category in Atlas, again, with a fit on M gamma gamma. And as you see, this case is much more different than the previous ones. There are very few events. So the sensitivity is clearly dominated by the limited number of events. But still, the sensitivity is similar to previous channels. CMS sets a sensitivity to 5.5 times the standard model, Atlas to 5 times the standard model. So again, we have channels which are in the same ballpark and will all contribute to an overall sensitivity to this process. We don't have time, just wanted to mention that there are many more channels we have seen in the map at the beginning. Just an illustration of, for example, BBZZ2 for leptons, channels which target essentially BBWW production in Atlas and in CMS here with 2 lepton or 2 lepton and 1 lepton. The famous multi-lepton and photon analysis, which you see is very complicated because combines several final states and try to map them into analysis channels, so essentially signature that you can see in the detector, and of course it requires a big effort to make sure that all these channels are controlled, are well modeled, and they are effectively combined. But you say that these channels are less sensitive than the others, but altogether they contribute to maximize the experimental sensitivity to HH. So there's really a big effort to study the Higgs in all the possible decay channels at the LHC. So here is a summary of the 412 results, essentially putting together all the analyses that we have seen so far and the ones we have not yet seen. On the left is the summary from Atlas, which sets a combined limit of 2.4 times the standard model expected and an observation of 2.9. And on the right, the same for CMS with a combination of a subset of these channels indicated by this symbol, which again is sensitive to about 2.5 times the standard model with an observation of 3.4. And you see BB gamma gamma, BBB, and BB tau tau are the 3 dominant channels in both experiments, but the other contribute with together about the sensitivity of each of these individual channels. So it's really important to study as many channels as possible. These results are limited by statistical uncertainty, so you can expect they will improve with more data. The leading systematic is the theoretical uncertainty on the Higgs cross section. There's an uncertainty of about 20% because of the top scheme, so surprising is the leading uncertainty now. And then the background of single Higgs plus heavy flavor for the background normalization. There are some experimental systematic uncertainty which are important, for example, the background modeling, but overall these are subdominant with respect to statistical uncertainties. And as you can imagine, there's an ongoing effort to combine ATLAS and CMS because you can really get the best sensitivity to the Higgs and the LHC by combining the results from the two experiments. Now, about the self-coupling, so kappa lambda or lambda, here's the summary. On the left, you see a scan of the excluded cross-section by CMS as function of kappa lambda. And here you clearly see the famous effect of the interference that we have seen before. So the standard model sits here, where kappa lambda is 1. And when you are in the maximal interference cross-section, you start to have an increased sensitivity because you are populating the high mass invariant spectrum part of the Higgs plane. Then around kappa lambda 4 to 5, the interference kicks in and you have a lot of events at low invariant mass, which is a difficult region experimentally to probe because the acceptance is reduced. And then asymptotically for large values kappa lambda in both directions, this limit stays the same. So if you intersect this upper limit with the total cross-section, you can say that kappa lambda is excluded to be outside of the range -1.2 to 6.5. Similarly for ATLAS, here, there's a scan in terms of likelihood instead. So you scan the log likelihood as function of the parameter kappa lambda. And you can set a constraint observed, which is between -1.2 and 7.2 for kappa lambda, and an expectation which is around -1.6 to 6.5. And you see that the channels are complementary. So the way they contribute to kappa lambda is different, to the constraint is different depending on whether we are on the positive side or on the negative side. So there's really a benefit in combining them. The sensitivity is maximized with the combination, but the region which is between, let's say 1 to 5, so this region here is going to be the hardest to probe experimentally because the cross-section is very small, and the spectrum is very soft. So this is the region that we're trying to more and more approach with the increasing data sets. And I think it's worth looking a bit back and seeing how this evolution of the results was impressive over the run 2. Now we are almost used to see 2 times the standard model, 2.5 times the standard model, but this is something that was really unexpected until even just a few years ago. And this plot on the left, maybe it's a bit busy, so I'll try to guide you, but essentially summarizes the limit on the mu HH from ATLAS in red and from CMS in blue for the 3 main channels, so for B beta tau, for B beta tau, maybe gamma gamma, as function of integrated luminosity, because there were essentially 3 iterations of this analysis. The very first at the run 2, done with between 2 and 3 inverse femtobarn, which are here, not even done in all channels. They were really the first pass at the LHC dataset to search for the Higgs. The 2016 analysis done with about 36 inverse femtobarn, and then the full run 2, the one that we have just seen with 140 femtobarn. Now, these gray lines that you see here are the luminosity scaling. So is how much the sensitivity would improve if you were scaling just by the luminosity. And you see that at every iteration, we've taken something between a factor of 2 to a factor of 3 improvement on top of the luminosity scaling itself. So we improve beyond this, which is the equivalent of having run between 4 and 9 times more. So this scaling really exceeded, the sensitivity really exceeded the luminosity scaling. And it's something not common in analysis, and it really shows how much work has gone into optimizing these results. And I like to show this because I think it's quite representative here. These are just sentences taken from paper from 10 to 20 years ago. That were saying that essentially, for example, for the Higgs 2,4b, was too bad to be a suitable channel, suffer from huge QCD backgrounds, is overwhelmed at the LHC by a huge background, and is essentially impossible. And I was myself writing one of these sentences. It was in my master thesis because that was at the time the feeling for me was just too much background, and it was impossible to study. And today is one of the leading channel in the Higgs. So this really illustrates how impressive was the experimental improvement over the past few years. And if you want to know what enabled this improvement, essentially we have improved analysis techniques. So we have more data, so we can better explore the phase space with categories, selection, and better use the events. Here is an example of DNN-based regression of the mass in CMS. There's a similar thing in ATLAS, which essentially enables to shrink the peak, and so to have better identification of the BB system. And then we have improved object identification. Just a few examples from run 2 are the identification of taus. So deep tau, for example, in CMS to identify hadronic taus, DNN-based identification for B-tagging, or a neural network for identifying resonance decay into BB bar. And these are key elements because the performance of this object directly transports into the analysis, and often with some power, like the power of 4 for B-tagging in a 4B analysis. And behind all this, there are modern machine learning methods that are really becoming a key element in both areas of analysis and of object identification. So these are really an essential element that is going to be more and more developed for the upcoming results. Just one mention about the indirect constraints from single Higgs production. Essentially, you can use single Higgs as a precision tool to look for lambda, because you can use NLO effects. So you can produce single Higgs here, and you can model the effects of loop level correction in the production of single Higgs in TTH, VBF, VH, and gluon fusion. And this impacts both the total production cross section. You see the largest effect is for TTH, but it's sizable for most production modes, and impacts the branching fraction. So you tend to have a decrease of the fermionic decays and an increase of the bosonic decays as function of kappa lambda. You also have an impact from interferential distribution. So again, the largest effect is from TTH, is the change in the PT distribution of the Higgs as function of the PT. And so you can use single Higgs measurement to try to extract this information and combine it and put a constraint on the value of the self-cap. And this is the result that is done in an Higgs plus di-Higgs combination. And you have a twofold benefit. On the di-Higgs production, what has been hidden so far is that we just focus on the self-coupling, but actually the differential cross-section scales like the ratio of the kappa lambda to kappa top, because your cross-section scales like kappa top to the 4 times 1 plus r squared, where r is this kappa lambda to kappa top. So you have very large degeneracy between kappa lambda and kappa top in this figure. And this you can see from the di-Higgs only constraint in this plane, which is indeed kappa lambda versus kappa top, where essentially you have a degenerate direction for the di-Higgs only analysis. But once you include single Higgs, you lift this degeneracy because you can measure kappa top from independent analysis. And then you can get a very robust determination of kappa lambda. And then once you go instead in single Higgs determination, you cannot really disentangle whether your effects come from kappa lambda or from other change of coupling. So by combining single Higgs and di-Higgs, you can lift this degeneracy and you can improve overall your combined limit, as you see here in these CMS results. Now, in all this, what we see is that single Higgs plays a role, but the main driver for the sensitivity is still double Higgs. So we benefit from pushing more and more the di-Higgs analysis in the runtime. Now, coming to the third part of this presentation is essentially how can use di-Higgs as a proof for new physics. So new physics is very high scale in EFT, vector boson fusion production, and resonance production. I'll try to be a bit fast to make sure we stay in time, but effective field theories, essentially, we are not guaranteed that this new physics might be at the direct energy scale of the LHC. It may be beyond the direct energy reach. So we can parameterize the effects at low energy in what is called the effective field theory framework. So you model the effect of this new physics generically at low scales. And this results in modification of the existing standard model interaction, as you see here, but also new effective contact interaction that if you had more energy, you could resolve and see some ultraviolet structure that is responsible for these contact interactions. Now, in di-Higgs, we explore two different types of effective field theory because you can decide how you want to build this EFT. There is the SMEFT, which is the standard model effective field theory, when the standard model is expanded with higher dimension operators, and we stop at dimension 6. This preserves the standard model symmetry, so the Higgs is still a doublet, and essentially generates this operator that will give rise to this type of interaction, but these interactions are correlated. So for example, the GGH and GGHH interaction, or TTH and TTHH interactions have strengths that are correlated because it's the same operator behind. And this means that there's an interplay between what you can do in di-Higgs and what you can do in single Higgs, for example, measurements. A more generic frame is the EFT, which is a more generic extension of the standard model with more parameters. So every interaction is essentially an independent parameter. You see the Lagrangian here, but it maps one-to-one to each of these. So you have something more complicated, but with more degrees of freedom versus something a bit more simple, even though it's many operators, thousands of operators, but which can be more easily studied across several type of processes. And this is an overview of the result that we do in EFT. So the effects are very large. It's not easy to model them because the effect of EFTs are both on the total cross-section and differential cross-sections. So these are modeled in the analysis described in this work. And this is a constraint by Atlas in the theory on the GGHH versus TTHH interaction. You see there's some tension with respect to the standard model. Actually, it's compatible within 3 sigma with the standard model. This is because of an excess in at low mass in 4B. So this is understood. And as you can imagine, you cannot really set further constraints on this because all these operators are somehow degenerate. You cannot disentangle effects from all these operators at once. So we focus just on the 2 ones which involve directly the Higgs vertices. But this benefits in the future, for example, of having new decay modes, like production modes, like TTHH, for example. On the other side, we have a result in SMEFT in BB gamma gamma from the Atlas analysis. You see this constraint CH box versus CH. It's compatible with the standard model, but one important thing is that we are at the edge of the FT validity, essentially, because under some approximation, we have very large variation of these operators, and we, for example, we cannot disentangle linear plus quadratic boundaries. So we cannot do a full 5D fit here, and likely inputting the Higgs as in this MEF fit is something that we can benefit from. Now, vector boson fusion, actually. Vector boson fusion is the second production mode at the LHC. The cross-section is very small. It's about 1.7 femtobarn. But it has this unique access to the kappa 2V interaction. So you have the coupling of 2 vector boson to 2 Higgs boson that you can see here. And in the standard model, these are related. This is an important point. So they are related because they come from the same mechanism, and they are related. The VVHH interaction, the VVH interaction have the same strength, essentially, or can vary in the same way if the Higgs is a doublet. So if there is new physics that alters this equilibrium between the two, there's a spectacular non-cancellation of these diagrams, which essentially brings the production cross-section to be very large. You can see by a variation of just factor of 1 of this coupling, you have change in the cross-section of a factor of 10 to 100. And this cross-section is essentially at very high invariant mass. So you have a double boost in the experimental sensitivity because you have high mass where it is easy to see these events, and you have a very large cross-section. So this has been studied at the LHC. The goal is to, again, search for new physics by searching for processes which could alter this cancellation, which otherwise suppresses VBF. And the leading channel is 4B because the process is rare, using boosted jets because you have a lot of events at high mass. So the signature is like this, as illustrated here. You have a high delta eta jet pair, and you have the 2 jets from the 2 boosted jets for the 2 Higgs decays that are used to select the events. Essentially, they give you high branching fraction, and you focus on events at high Higgs boson PT. Maybe I can skip this, but essentially key ingredient in this analysis is the jet tagging, boosted jet tagging, which has seen very impressive improvement in the past years, thanks to machine learning techniques, and is a key ingredient of the analysis. By using this, we can really push the sensitivity of the methods because we use the identification of this jet to separate from the main background, which is QCD. And this is the result, the experimental result. As you can see, we put a very tight constraint on this coupling because CMS excludes the kappa 2V0 hypothesis at the 6.6 sigma level, assuming the other interaction as a standard model. Atlas sets in the combination a similar constraint. Essentially, kappa 2V must lie between 0.6 and 1.5. This is driven by the 4B analysis. And is a strong implication on new physics that are yet to be fully studied. The interpretation are yet to be fully studied. But for example, it was shown that for new physics, which is parameterized with effective field theory at dimension 8, this is compatible with vector boson scattering. And it is something that is not yet explored in experimental analysis that can be done in the LHC runtime. Maybe some word on resonance production. I'll be very fast on this because I think we're running out of time. But you can also use the Higgs to search directly for new physics through the decays of new resonances to the Higgs pair. And this is a common thing in many extended scalar sector models, where essentially this extended scalar sector predict additional scalars which can couple to Higgs and decay to Higgs boson pair or Higgs plus another particle. The challenge is that you need to cover, again, a broad range of masses. So channels are combined to cover the full plane. On the left, you see the Atlas result, on the right, the CMS result. And you really see that at low mass, BB gamma gamma is the most sensitive, BB tau tau leads in the medium mass range, and 4B leads in the high mass range because, again, similar to VPF because of the boosted analysis. There are many interpretations that can be done, essentially constraining new physics models. Similar, you can search for production of Higgs plus another scalar. And here you're really spanning a very big phase space and to cover extended scalar sectors. But you see here again, the combination of BB tau tau, BB gamma gamma, and 4B by CMS with one particle going, the new particle to BB, and the Higgs going to BB gamma gamma and tau tau. Unfortunately, no significant excess is seen so far. Now, final word on the future prospects. What we can expect to do in the Higgs in short term, medium term, and long term. The short term is clearly the event 3. Analysis is already ongoing, so it's something it's going to be done soon. First of all, it's an opportunity to maximize the analysis sensitivity. And then it's an opportunity to expand on the interpretation on the physics reach. We can study new production modes, study FT, study interplay between VBF Higgs and vector boson scattering. We will benefit analysis from a lot of improvements. On one side, on the object. So this illustrates the improvement in the rejection of background from new BJ identification methods. This is what was used for existing analysis, and this is what we can use in more recent analysis. So you see there's a factor of 3 improvement in the performance, essentially. We have improved triggers to select more events in the hadronic signature, like 4B and BB tau tau. So if we take these numbers together, we know that event 2, each experiment has sensitivity to about 2.4 times the standard model. So combined event 2, scaling by the event 3, essentially we expect each experiment to do about 1.4 times the standard model. Together combined is going to be 1 time the standard model, Atlas plus CMS. If we still can have the similar improvements as we have observed now, we might have an evidence for the Higgs at LHC event 3, which is something really totally unforeseen, was seen as something already difficult at LHC. It's going to be difficult, but it's a really exciting opportunity for the Higgs physics in the event 3. Now, in the high luminosity, which is going to start with the first bin late 2029, hopefully, we have about 3 Barnov data that we can use. It's really the ultimate possibility to study with precision Higgs physics and to study the Higgs with the largest data set. It's very challenging because the luminosity is extremely high. We have about 200 simultaneous polar interaction per bunch crossing. And in the Higgs, we rely on essentially soft objects. So we need to study the low MHH regime to measure the self-coupling. And you see, for example, every few GV of increased threshold are going to be a quite relevant loss in the significance, for example, of the Higgs to 4B. So there's an ambitious program of upgrade which is in place to tackle these challenges, to maintain and improve the performance of the experiments in the LHC. And the current prospects that were derived a few years ago are that essentially combined Atlas and CMS, we should reach a significance of about 4 sigma, which is just short of 5, with a precision on the self-coupling of about 50% and 100% at 1 and 2 sigma, respectively. This is the summary from a few years ago. It's clear that we need to combine several channels together to reach the maximal sensitivity. It's also clear nowadays that these projections are very conservative because we've seen these were based on the 2016 analysis, the early results. We've seen how much this analysis improved, and more recent projections have already exceeded this, essentially, as you can see, for example, in this Atlas work. So there's an ongoing effort to update this projection for the next European strategy, and hopefully we'll show with this prospect that we can actually go closer to the 5 sigma target for the Higgs. Beyond the LHC, the picture is a bit different. We have 2 options. We have essentially high energy proton-proton machines. These are really the Higgs factories. They will give us more than 30 million Higgs events to study because you have an increase of 33 times in the cross section, 10 times in the luminosity. So these are the machine for the ultimate precision on lambda. But for the plus and minus machine, you can study the Higgs only at very high center of mass energy, because essentially you can use either the vector boson fusion mechanism or the Z-Thalium mechanism, but both of them are require at least 400 to 500 GeV of energy. So this is possible only in high energy linear colliders so far. And otherwise, you need to study indirectly the Higgs from single Higgs production. So now combining all this together, the current expected sensitivity is summarized in this plot. And you see the sensitivity for the various future colliders. In solid bar, there is the sensitivity from direct HH and dashed from indirect from single Higgs. And what I want to show is that all these measurements are combined with the expected sensitivity from HL-LHC, which is here. So essentially, for a very long time, the HL-LHC result is going to be the leading result on the self-coupling, and is going to be the reference number for all the future studies of the self-coupling. So what we can do with the HL-LHC data is really going to be an important legacy for the long-term future, and something that we really need to do with high sensitivity and push in order to have the best determination of this coupling with the large data set over the next decade. All right, so sorry for taking maybe a few more minutes than expected, but in conclusion, I hope I convince you, or I'll be able to show that studying the self-coupling is important because it's at the core of the standard model. The shape of the Higgs potential is connected to this. It's difficult to measure the self-coupling from the Higgs because the process is very rare. And so to tackle this, we need to explore and combine several decay channels. But at the same time, we can also use the Higgs as a tool to look for new physics, both at very high scale, indirectly, or directly with the resonant production. And I think the key message here is that the effort that is done by Atlas and CMS to study the Higgs is really impressive. Many decay channels are studied, analyses have improved much faster than anticipated, and so far each experiment is sensitive to about 2.4 times the standard model production. It was really not anticipated. So with this, I think we can be very optimistic for the future. The prospects are excellent. There are going to be important challenges to tackle with the upgrades, but we might reach an evidence for the Higgs at the run 3, and we'll likely reach an observation for the HL-LHC. So the Higgs and lambda HHS is really one of the key goals for the short-term and long-term program of essentially particle physics at accelerators. Thank you.